I'm Diptiman. I'm a staff developer advocate at Confluent. And today, I'm going to open up my kitchen for Flink SQL recipes. And as I told you, I got the code ready on GitHub. So if you want to see it, if you want to do it yourself, by all means, join with your laptop. But the topic that I'm going to talk about today is how to do Python data engineering with Flink. And when I say Flink, I mean both PyFlink or very specifically PyFlink Table API. And I'll go deeper into what that is, which is like a data frame equivalent in Flink SQL, and when you can query your Kafka streams. And we would also see how Flink SQL works on its own, right? So this is the GitHub link for code. So if you can do it once you're back home. You can do it now. And then there is if you want to run your Flink SQL, by all means, you can run it on Confluent Cloud. There is a promo code which gives you like a 30-day payment delay, so you don't have to show your credit card, and you get like a $400 worth of credit running Flink SQL. Quickly, how it's all set up. So you register with that promo code on confluent.cloud, HTTPS confluent.cloud, and then you click environments. There would be a default environment created for you. You click on Flink on top, like here on top, and then that opens up the SQL workspace where you could write your queries. So that's one way. Or else what you could do is you could just create a Python 3.11.x virtual environment and just do a pip install Apache Flink. That's it. You don't need anything else. There is only one dependency, that's Apache Flink, and I'll show you how you would run it. So that being the premise, and we will come back to the premise, the talk today is just to enlighten all of us in terms of how do we do Python data engineering with Apache Flink. Now, a quick raise of hands in terms of how many of you have used Kafka before, like beginner to advanced? Okay, perfect. Fairly large. How many of you have used PyFlink before? 2, 3, 4, 5, 6. Perfect. So then I think I'm in the right room. So we are going absolutely deep into PyFlink Table API and how it lets you do Python data engineering, right? But before that, let's set the stage quickly with a Kafka 101. Like very, very quickly, let me run through it. So Kafka lets you store your stream. So it's a streaming storage framework. And just like there is a table for a database, you have files for Hadoop as the core abstraction. For Kafka, the core abstraction is the log. So it's a log which is immutable, and it is distributed across brokers or across servers, and new messages are added at the very end. Why is it fast? Because the insertion is big O1. So what happens is each message has a very roughly header, a timestamp, a key, and value, while the mandatory things are only the value and the topic name, but the rest are pretty important things as well. Topics are the namespace isolation contexts within a Kafka broker. So just like a database table, you could have a click, an order table, a customer table. You could have a click topic, an order topic, or a customer topic. Topics are similar to concept in just as tables in databases. And then topics are broken down into partitions. And partitions are the unit of parallelism. So if you want to add more messages in your Kafka topics, you get more partitions. If you don't want more messages, you could actually have less partitions, except to the point that it does serve your fault tolerance needs, right? And messages within a partition are guaranteed to be in order, in sequence. So it's a pub-sub kind of an architecture where producers publish data to Kafka brokers. Kafka brokers acts as the stream storage, uses the distributed commit log for storing these messages, and then you could have consumers. So messages are added at the end of the log when the producers are producing those messages. Messages have those index which is known as offsets, so that you understand where in the partition your message lies, so that you could extract it, and consumers have the knowledge of that position of each of those messages with the correct offset. Now, each consumer, after consuming, also lets the broker know till what point the consumer has processed these messages, which is normally known as consumer offset, and syncing the consumer offset with the broker using something known as a commit sync or async commit. While I'm producing to Kafka, I could decide to have a key, or I could decide not to have a key. If there is a key missing, then Kafka broker takes these messages from these producers and distributes these messages across all your partitions within a topic. Now, if you do have a key, then we calculate the hash function using this formula, the Murmur2 protocol, Murmur2 algorithm, sorry, and then we decide which partition it goes to. All messages with the same key goes to the same partition. While consuming, I could have a single consumer, or I could have multiple consumers as well. I could have consumers grouped together so that they do one job well together in one group. And then this producer, broker, and consumer, this pub-sub, becomes a linearly scalable architecture because you could just add more and more servers or brokers horizontally and increase the throughput. Now, how do you get fault tolerance? Kafka provides replication, which ensures that your messages are all fault tolerant. So if this is, let's say, a regular setup of how your topics and partitions are assigned across 4 brokers, replication would ensure that fault tolerance is inbuilt within the design. So if the last broker goes down, then what happens is your broker 2 topic X partition 4 becomes the main topic, the main partition, right? So these partitions have a leader-follower strategy. So the followers would get data from the leader and all that stuff. So essentially what we've seen is it's a log, similar to a traditional messaging system, but with far better scalability, throughput, and built-in fault tolerance, right? So that's the big picture. I have a broker, I have a producer or set of producers, I have my consumers, the brokers have topics, which are like tables, and these topics have partitions, which are my unit of parallelism, and then partitions are actually abstracted out physically as something known as segment files. But then this is just a refresher. We don't want to go absolutely deep into what happens. I mean, if you look at the producer, it's a very busy person, really. It doesn't look like if you look at a producer code, but then all these things keep on happening. So there is a serializer which takes these messages and then converts it into byte array forms. There's a partitioner which ensures that these messages are assigned to the right partitions. And then there is a batching mechanism which ensures that you get the desired throughput that you deserve. And then there is a retry mechanism, so you could actually have sophisticated retries after a certain point and then gracefully degrade. For consumers, it's an eternal poll for loop which keeps on running, and it extracts data from the brokers, from the partitions, topic partitions, and of course it could work in groups or it could work alone, and then internally they also collaborate, and then the broker keeps a heartbeat to check whether a consumer has gone down and stuff like that. And then the job of the consumer is to ensure that it commits those offsets so that everybody is aware till which point the consumer has read those messages. Now, having understood what Kafka does, it lets you store your stream. Let's move into Flink. Now, what is the reason why we use Flink at all? We use Flink to transform the streaming data in real time, just in time. We want to query, we want to enrich, we want to apply sophisticated transformations on that streaming data, real time. and get it across to another, maybe a Kafka topic, quickly so that the downstream can start accessing it. So that's what the goal is. I want to transform my streaming data real time, right? And largely it has been driven by the industry. So in today's consumers, they expect real-time services. So, you want to know whether somebody has liked your Facebook post or a LinkedIn post. You want to know if you have paid your electricity bill, whether you're getting a ACK message from the power supply distribution provider, et cetera, right? Now, when we talk about this streaming data, we actually talk about these events, right? Event stream processing, that's what we process. What is an event? Event has a what and a when. It has a state and it has a timestamp. So these are good examples. So I could have an event coming from an IoT sensor, which could have a device ID, and then a set of values, which is constrained within that single packet, which actually produces the state of that event, state of the sensor, that specific time. Or I could have a business process change. Somebody's loan application got approved, and with the customer ID as the key, or the loan application ID as the key, an event might be produced. Or it could be an user interaction. If somebody is clicking on let's say, one website on the cart, that event goes out, and you have some sort of a clickstream data which tries to capture that event, right? So we understood what an event is. So at a minimum, it has a key and a value. Of course, for Kafka, the mandatory things, as I told you, are the topic and the value, and the rest are non-mandatory. It's still optional, but we strongly encourage to put the key in stuff so that you can do a lot of good group by kind of operations once your messages start appearing in Flink. So now that we understand what an event is, let's look at what an event stream is. So an event stream, unlike a database table, is an unbounded context of append log only data, which is getting all these events getting appended to the stream, right? So streaming data or an event stream is nothing but an unbounded table. In a database table, you could do a select count star, maybe 5 times, and 90% chance that you would get the same result. But you won't get that in a stream, because the result keeps on changing, right? So events are ingested perpetually till you stop the producer or till the processor goes down, right? So in those scenarios, how do we extract insights from these streams? All Kafka is producing is coming to my topic, and I want to transform, I want to extract insights, I want to do group by, I want to do joins. So what we do is from now, like from a time now, we go back to the stream, and we do have the capability to look back, and then we try to put time boundaries. And we'll go deeper into what time boundaries are, but then time boundaries logically segregate these streams, this streaming data from now to the past, and lets us query to gather insights. And while from now to the future, streaming data keeps on adding events to my Kafka stream. So Flink comes in as a streaming data processor because it has sophisticated DSL capabilities. You can use Python, you can use Java, although I focus on Python. You could write ANSI SQL 2016 compliance SQL, which would help you derive this insights out. And you could have aggregations as well, pretty sophisticated ones. So today I'm going to talk about how real-time services are being done using stream processing, and my weapon of choice is Python and SQL, PyFlink and Flink SQL. And just to give you a quick example of how it might look like in real world, we might have IoT sensors in a photovoltaic farm in a ground, and these would push data to an aggregator or a producer, and the producer would push this data to an Apache Kafka topic. And my Apache Flink application, whether it's Flink SQL or PyFlink, would work on that topic, give me extract the insights from those topics, put it in a new topic which is aggregated, and then I have all my mechanisms using Kafka Connect, etc., to push my data into something like an Elasticsearch index. And I could just attach a Kibana dashboard, and I get my real-time dashboard updated every 5 seconds. So now that we understand what an event is, what an event stream is, we understood a little bit about how Flink comes into the picture. Let's understand the anatomy of a Flink cluster. So a Flink cluster is an MPP cluster, massively parallel processing cluster. So the Flink client takes this input, parses the data, and then creates a job graph, and then it pushes that job graph to your job manager, to our Flink cluster job manager. And the job manager is the brain behind the whole operations. So based on the kind of the job graph submitted by the client, it would spin up these task managers. Task managers are multi-threaded Java applications where each task manager can granularly create slots for running each of these tasks or subtasks. Now, a quick point, Flink actually intelligently chains these subtasks into tasks, right? And each task is then executed by a single thread within the task manager. So the example that I've given, so I have a source operator, and the source operator has a map function applied on it. I have another source operator with a map. Both are applied a group by, it's a key by, and then I use a sync operator. So there are 5 subtasks being executed by 5 parallel threads. And you don't do anything of your own. Flink is intelligent enough to do it. Although it's part of the infra layer, but let's understand how it works internally so that we also have a chance to debug in case something goes south. And as I told you, it has task slots. Each task slot represents a fixed subset of the resources of your task manager. So with the 3 slots, it would dedicate 1/3 of its managed memory to each slot. Now, do you run this infra yourself? You definitely can. It supports Mesos, Yarn, K8s, etc. Or you could use managed services. Like Confluent Cloud, we have Flink SQL, the one that I showed. Now that we understand the cluster and how a Flink cluster works, let's understand this concept of Flink dynamic table, because this is the most important for today's session. So Flink dynamic table creates or mimics your Kafka topic. So while there are many other APIs within Flink, and process functions and data stream are the lowest level APIs, I talk about table API and Flink SQL because it lets you work with Flink dynamic tables. A dynamic table mimics or abstracts your Kafka topic, right? So what happens is, let's say I have my streaming data on a Kafka topic. A Flink dynamic table would let me query the same streaming data as a database table on SQL. So I have Murray, Bob, they are clicking on specific URLs, and then that comes out with the schema intact on my Flink dynamic table as user, created time, and URL. And as I told you, it's an unbounded table, right? So it's an append-only table, so rows keep on getting added. But then when I apply a query, whether through Flink SQL or using PyFlink, the query works on the dynamic table, keeps state for aggregations, joins, stateful operations, if I might say so, and then it emits another dynamic table as the result, which is the result of your select query or the result of your PyFlink operation that you're acting on. And then that dynamic table could also act as a Kafka topic, which is why we call this a stream table duality. So quickly, let's recap it. So a dynamic table would change over time because data keeps on getting added. Querying dynamic tables would yield a continuous query. That query perpetually keeps on running. And then a continuous query would produce another Flink dynamic table, which is like the result of my query. And that can appear as a Kafka topic to me, so that I could have my downstream applications pulling the data. But this time the data is transformed, aggregated, deduplicated, joined, null value removed, and all those things. So again, going back to the example, you can actually write queries like this, which is a group by user. And then what happens is, every time there's a new record which keeps on coming on your Kafka topic, your resultant table would keeps on showing the new data. Now that's an append-only table, so it keeps on updating and appending or rather upserting the data. So that's one way, right? What we understood is, I have my Flink dynamic table, data coming in from my Kafka topic. I could create a new table and just do an insert. So whatever happens on this table, Flink dynamic table would store that again, right? So that's one stream table duality case. The next case is when I do an update operation or a delete operation on my source table, then what happens is your resultant Flink dynamic table would actually have two steps. One to retract the data, and the next to update, which is commonly known as upserting the data, right? So we have an append-only stream, so a Flink dynamic table just keeps on getting added with rows, or we could have an upsert or retract stream. Both are similar. Upsert is a little bit more efficient, but then what it does is it retracts the message and updates the value. Now, having understood what that is, this is what I wanted to focus for today. But before we jump in, let's understand what these things are. So we would go back to this SQL which you right now you saw. So let's understand what these things are, right? What are these window functions? So as I told you, I'm sitting at now, and then I have my past data, which is all my Kafka topic data, which has been accumulating till now, and I want to process that data. So normally I would process by injecting these time barriers or temporal controls, as we call it, right? And these time barriers are known as window function, windowing. Now, these are also called windowing TVFs, table valued functions, which is the ANSYS SQL 2016 polymorphic table function equivalent, PTFs. But let's quickly understand what that is, right? So this is an event continuum. So 0th hour, 1st hour, 2nd hour, 2, 3, 4, 5. And let's say these are the events which are getting accumulated. Between 0 and 1st hour, 4, 1st and 2nd hour, 2, like that. So what a tumbling window here would do is, a window would get injected on this event continuum with a size of 1 hour, s equal to 1. So the output of that tumbling window for 0 to 1 would be 4, 1 to 2 would be 2, 2 to 3 would be 3, 3 to 4 would be 0, and 4 to 5 would be 1. And these are discrete, they never overlap. So a tumbling window with a size of 1 hour. What's a good example? A good example is, let's say, a toll booth where you have a camera and you ask the question, how many vehicles have been passing the toll booth, right? So if we don't even do windowing, we could ask how many vehicles were passing, and you could give me maybe in one day 500 vehicles have passed, or somebody could give you maybe in the last 5 minutes 20 vehicles have passed, right? So a better way, so what you really lack in these kinds of insights or answers is you don't get the variability of time within the answers. So your insights would lack that variation over time. So the right question to ask is, how many vehicles crossed this toll booth camera in the last 15 minutes? So that 15-minute interval would give you a tumbling window result. You get it now? Now there is another concept called a hopping window. Hopping window, what happens is, there is this slider, but look at that slider, although it has a size of 1 hour, it moves every 15 minutes. So essentially what happens is, the insight that you start getting out of this is how many vehicles passed this toll booth camera every 1 hour, and please keep me updated with the value every 15 minutes. So this is called smoothing of the averages. Right? I mean, in stock tickers, there's an SMA, we use a lot of SMAs. It's similar to that. So here, if you look at it, hopping window has a size of 1 and a hop slider of 15 minutes, which is 0.25 hours. Now, if you again go back to the tumbling window, you would see that a tumbling window is nothing but a special case of a hopping window where the slider and the hop merges. So here, S equal to 1, H equal to 1. While in a hopping window, S equal to 1, H equal to 1/4 of an hour. Get it? So these are good for the next set of insights, as I told you, that how many vehicles crossed, please keep me updated every 15 minutes. Now there are two more windows, session window and cumulate window, but I would just give you a brief of what a session window is. I gave you the code. If you have taken a screenshot of the GitHub QR, there is a query which is already there, both in PyFlink as well as in Flink SQL, and we'll revisit it. So a session window comes in very handy if you want to measure the inactivity of a specific window. So let's say a user logged in to your website. The user was browsing some of your catalog, some of your products, but then the user has logged out. And then the user again logged back in, let's say 30 minutes later. So I want to capture these kinds of events, and I want to get an insight, okay, how many users were active on my website less than 15 minutes every day. That's where session windows would come in. Because session windows would close once the inactivity window expires. So if I put an inactivity window of 15 minutes, so after 15 minutes, so here the inactivity window is 30 minutes. So after 30 minutes, it would close, and a new session window would open. Now, as you've understood, we've covered the group by, and now we've covered the window function. Now let's understand how it helps us, right? So let's get back to the query that we wrote, that we were trying to get, right? So it's clickstream data. I have my user, my creation time, my URL, and I want to write a query where I want to know every hour one distinct user has logged in or clicked how many times. So from the window of 12 to 1 p.m., Marie had clicked thrice, Bob has once. From 1 to 2, Bob had 1, Liz 2, etc. And how do we show it? We show it using this syntax. We put the tumble end and the interval as 1 hour, and then we do a group by user. Again, we'll go back to the query. So quickly doing a recap, as I told you, these are table valued functions. These are called table valued functions because these are functions which lets you use tables as parameters, relational tables as parameters, right? This is part of the ANSYS SQL 2016 standard, by the way, and Flink provides 4 such built-in table windowing table valued functions: tumble, hop, cumulate, and sessions. As I told you, this is a tumble example, discrete non-overlapping windows, and this is a hopping window example where the window overlaps. So I do have a Kafka PyFlink getting started. By all means, please go through it. It would get you started with Kafka. It would get you started with PyFlink, etc. Now let's understand and go a little deeper into how the code is being written, right? So a normal Flink data flow would have, let's say, 2 Flink dynamic tables, a transaction and a customer, and I could actually do an insert into sync by selecting distinct transactions and then joining it with the customers. So I could have a transaction ID, customer name, and transaction amount, and then push it to the sink. So this is how a table API looked like. I'm not too sure if you can see it from the back, But then that's the QR to get you started, the GitHub code repo and the blog. So this is how it looks like. So I was talking about the stream table duality, right? So this is your Flink dynamic table, and look how the connector is Kafka. I have a topic already created. I have my bootstrap server provided. Then it becomes a Flink dynamic table for me, and I could actually have a table when I do a tm.from path and sensor readings. Now, what's the beauty behind it is then I could use something like this, which is a Pythonic table API DSL, which lets you create the relational operation, the window TVF, the table valued function, which will let you do the group by, right? So here I do a tumble for 30 seconds on the processing time of the sensor readings topic or Flink dynamic table. As I told you, both are the same. It's a stream table duality. I would group by the device ID, and what I'm really looking at is I want to know the sum of the battery charge over a period of 30 seconds for these devices. So I want to know the charge consumed by each device every 30 seconds, non-overlapping, per user, per device ID. So that's the table API way of doing it. If you want to do it using a Fluent Pythonic table API, this is your way. If you want to do it using Flink SQL, this is your way. Now remember, both generate the same explain plan. Both generate the same execution plan, physical execution plan, table API and Flink SQL. Both are relational, and both would give you the same thing. Now remember, when you apply your TVF, your Flink dynamic table in the result would actually have 3 columns inbuilt: a window start, a window end, and a window time. Just to give you more control over what's happening, and you can see when your event starts, and when your window starts, and when your window ends, and stuff like that. So as I told you, you could actually have an explain plan generated from your Python code, and it would generate the same thing. You could test it out both for Flink SQL and for table API. It generates the same set of physical execution plan, right? This is the Flink community. By all means, this is the Slack. Please join the Flink community. It would need your love to survive. And this is how we call that PyFlink loves Flink. But then I'm not done, so I wanted to show you how it looks like. I'll just. So all this code is actually there in GitHub. So this is the GitHub. So if you've already taken the QR code, this is the GitHub location. So this is there are 2 folders, one on Flink SQL, one on PyFlink. You could go to Flink SQL, and if you go to Flink SQL, you would have the respective code for that. And this is how you set yourself up on Confluent Cloud. If you want to see how aggregation looks like, now these are the aggregations. On Confluent Cloud, we already have four Flink dynamic tables created: clicks, orders, customers, and products. So you could write all these joins and have a look. These tables are created using something known as Flink Faker. It's a library which lets you create fake Flink tables with fake data. But then at the same time, you could also use Python. And if you're using Python, all you need to do is just add that Flink Faker jar, and it's freely available on GitHub. And my GitHub repo has all the coordinates for it. And then what you do is you create this table order, and you put the Faker library information so that the fields get populated. And then you could start writing your the code. Like here, I'm doing a sum, and I'm doing it over an interval of 15 seconds, and I'm grouped by just the window start and window end. So I just want to see the sum of total products sold, let's say, and it'll start running. So I hope I have internet, so it will start. So if you want to see it in action, demo time, always, yeah? So you look at the window start and the window end. So I have put a 15 seconds window, so it's 235.15 to 235.30. Another window would start once it reaches 245, and it'll go to 245 to, 235.30 to 235.45, and it'll keep on adding. So you get your total sum of products every 15 seconds. It would keep on running it. Just pip install Apache Flink, drop the jar file anywhere on your laptop, add it as an environment jar. It's there, the code is there in GitHub, and then you could test out all these queries. You could test out how these Flink relational operators work. Yeah, so that's it. I'm ready to take questions. I just hope that if you had like a stable enough internet, you could code along with me. But then I thought that I'll leave it to you, and you could actually take it back home and you could get started, both on Flink SQL or on PyFlink, all on your own. Thank you.
Hello.
Yes.
So how can I configure my source to read data from a particular partition when I'm using Flink SQL?
Could you please
how can I configure my source or consumer in Flink SQL to consume the data from a particular partition?
So what happens is, it's not a consumer per se. First of all, it's not a Kafka consumer, to be honest. So what Flink SQL does is it abstracts your Kafka topic. But then, if your question is, do I have controls on how do I read through partitions, all those latest offsets, and these are all possible today by providing in the with option. Remember, there was a with option?
Yeah. So when I discovered the Flink SQL documentation, there I could find that I can read data from a particular offset while using Flink SQL, but not from a particular partition. Data stream supports reading from a particular partition.
That's true. So as I told you, I mean, what happens is it's a relational table abstraction of your Kafka topic. So you have control on the earliest offset, latest offsets, etc. But you can't do seek and assign like you could normally do with a Kafka consumer. So it's a table API. It's mostly suited for SQL-like operations.
I have one more question regarding Hop window. So let's say I have a topic which is producing roughly around 4 to 5 million records per hour, and I want to aggregate data at a slide of 5 seconds and a size of 1 hour. So what I observe when I write the output to Kafka sync is, the initial windows I get a lag of let's say 4 to 5 seconds, but then that exponentially increases to 15 minutes, 20 minutes and so on. So what could be the root cause?
The root cause would be your watermark and idleness of the event source.
Idleness, timeout is set to 1 millisecond, watermark is set to 1 second to handle the out of orderness.
Yeah, so since your number of records are very high, so what would happen is your state store would grow very fast.
Correct.
And the watermark would take time to progress through all your Kafka partitions. So that is the reason. So what you need to do is you need to first you need to expand. First you need to expand the window size a little bit so that more data could be buffered and read in one go. And I don't know about the late order, whether you see late orders at all or not. Your watermark could decide also how this is propagated. How many partitions do you have in your topic?
30 partitions.
Sorry?
30 partitions.
30 partitions, yeah. So see, the point is, all these partitions would need to flow this watermark, and the least of these watermarks gets progressed. So that's why it is taking a lot of time. You could actually try out with a couple less partitions and see how it works out. Okay. If it's possible on your infrastructure. I mean, that's again a separate consideration.
Okay. So enabling checkpointing and state backend like RocksDB would help here, or it's?
Well, checkpointing is automatically enabled. You don't need to do anything about it. But your question is, you want to have your own state store? That's what your question is? Of course, it would help. But then that's a non-trivial thing to do, to be honest.
Okay.
Yeah.
Thank you.
Yes.
So one of the challenges is late arriving events for a previous Windows.
Yes.
Right. With Windows, it always looks on to the current window and oncoming windows that are about to come in.
Yes.
Is there a way to look back on previous windows and correct, let's say in this example, the sum?
No.
No.
So, see, that's the non-determinism that's inherent within all these windowing functions, right? So there is no deterministic way of figuring out by looking at my last watermark and see, well, you could have your custom watermark strategy by all means, but then it would never give you the same exact deterministic result every single time you want to do this operation. So let's say that's a problem with how you process dynamic streams. There is no other way of doing it.
Thank you.
Yeah.
Hello. So we're already using Rising Wave for real data streaming.
Yes.
So and we know this is a competitor for that. So what do you say, like how will I be benefited if I have to look into for this Flink? In which perspective?
Yeah, so I can't comment on Rising Wave, to be honest. So that's something you need to figure out. With Flink, what happens is, with all these managed services around Flink, which has become very commonplace nowadays, it's very easy to apply these transformations on streaming data. So if you already have Kafka, and if your downstream also uses some sort of streaming sync, it becomes very easy to apply these Flink transformations. Of course, Rising Wave does it in a completely different way, but then it doesn't stop you from experimenting as well. You could just go ahead, use your stream source, and experiment, and figure out if it addresses your concern or not. But what I'm trying to say is, Python data engineering is the most prevalent form of data engineering today, right? And you have the capability to write both Flink SQL as well as Table API. You could add these up in your streaming data pipeline. You could use Airflow operators, K8s operators as well. So it's a fairly balanced and well-provisioned suite of frameworks that you have. So it all depends on the kind of use case that you're using, and by all means do experiment and see if it works for you or not.
Sure.
Yeah. So I can take one more question, and then we'll have to prepare for the next session.
Hello. I do have one question.
Yes.
How to handle errors in Flink SQL? If you write Flink job in Java, you can have the side output to handle some of the error if there is some problem in the data or something. But if the Flink query fails, how to recover that?
So if Flink fails, you recover from your checkpoint.
Yeah.
That's one. That's the fault tolerant. So take that out of the question. But your bigger question was how to use side outputs, right?
Yeah.
Yeah, side inputs. So with Flink Table API, and of course, if you can create such sources, because here we have only dealt with Kafka, right? So here my only dynamic tables were Kafka. But by all means, you could have Flink tables which are batch as well. So you could have, let's say, a Postgres table, and you could operate on Flink, and then you could do a join with your dynamic table. But the question is, would that solve your problem or not? If you're using data stream, it becomes a bit easier, because what you could do is you could feed these side inputs directly into your data stream function. If you're using Table API, joins are your only option. So you have to use joins with your dynamic table and these. But then you have to be careful. It will not support all possible joins, right? If you're doing a side input kind of a operation for Flink. But there is no better way to do it on Table API. But then in data stream, it's a little easier to do.
Okay. And when the join will produce the result?
Sorry?
When the join will produce the result in the Flink?
Yeah, so when you run it, when the join runs, it would give rise to a dynamic table, right?
Yeah.
And you could then process that dynamic table either as a Kafka topic, or you could process it using any Flink actually putting this data into another sink. So you have two possible ways of doing it.
Okay. Yeah, thank you.
Sure. And I had one more question from the lady here, and we'll close it.
Hi. My question is related to the partitions again. There was a similar question earlier. If I have data which is in multiple partitions and it is not partitioned by key, then if I'm using a dynamic table, it does not really matter. The group by will still take care of it.
It would. It would intelligently take care of it. So essentially what happens is if you have multiple partitions and all these partitions are well distributed, Table API or Flink SQL, whichever you use, actually lets you treat it just as a database table. So all you're worried about is how the operations, the transformations are actually working, like your group bys and joins and window TVFs and PTFs, etc. So you don't really need to go down to the Kafka consumer kind of low-level code, which might be required for certain cases, but for, let's say, building a data pipeline, very rarely these cases would arise. So essentially, your Flink dynamic table would become just like a relational table for you, and you would be able to generate the source as you would be able to generate a result out of your query, and then use it as a sink, either as a Kafka topic or anywhere else.
Okay, in this case, we are using the SFTP connector, and we have orders with multiple line items.
Flink does have, so Flink does have a very, very well-defined SFTP connector, file-based connector.
So the same file has multiple line items for the file, so we need to kind of aggregate by the...
You can definitely do it with Table API.
So it doesn't matter. So it doesn't matter that it has multiple partitions.
No,
we don't have
doesn't matter.
Okay.
No, doesn't matter.
Okay, thanks.
Perfect. Thank you very much for your time and being patient with this session. So we'll close it here and we'll set up, we'll get prepared for the next one. Thanks again. Please don't forget to rate our sessions, and thanks again.